Hello and welcome to session 251 in the AISafety.com reading group. Tonight we'll be discussing the second part of the article A Generalist Agent by Scott Reed and others. This is a work done by DeepMind. When I say it's done by Scott Reed, it's actually with 21 other co-authors. And tonight we're talking about the second half of the paper. So we previously looked at Gato and saw some of its capabilities, and in this case we are trying to do in the second half of the paper we are looking at what can we learn about how Gato performs and with ablation studies and scaling in different parts. So we'll start with a scaling laws analysis. So here on the x-axis you have the number of tokens processed in hundreds of billions, and on the y-axis you have like what is the score, how good is this model actually performing on these 600 different tasks. And as you probably expect, the models, it looks like there's like a factor 3-4 in between these two, and it looks like there is like a different roughly the same order of magnitude improvement, and there seems to be a reasonably steady improvement according to a number of tokens processed. It looks a bit odd, it looks almost too regular for me when I look at this. Like I would have expected maybe some of the bigger models to learn slower. Like we expect that smaller models are less sample efficient, but on the other hand, of course, it's an easier problem getting to 40% than getting to 60%. And in this graph, it kind of seems like they're canceling each other out. I'm a bit confused. I mean, it's possible to look at this and say, oh, it looks like this graph is probably linear, and the difference between these are logarithmic. You could say something like that. It looks like there's not enough data here that we can really conclude anything strongly. Yeah. Also, like my catchphrase, this scaling laws is something that we have seen so incredibly many times, and it just looks like we are on a straight path towards having an AI that's competent enough to kill us. And so even though it looks very boring to again and again and again have the same kind of graphs, I do think that they're perhaps the most important thing. So one of the things that DeepMind cares a lot about is different kinds of generalization, out of distribution tasks, transfer learning, this kind of thing. And this is of course a question that they want to know, not just can it solve them, but can it do so efficiently. And they hold out 4 tasks. So out of the 604 tasks, they have 4 tasks that they choose not to train on. And then they wonder what is the best way to actually use Lambda. Lambda. We just talked about Lambda in the introduction. This has nothing to do with the Lambda model. This is the Gato model. And so the obvious way to think of how to do this would be to just have the prompt being some kind of a demonstration. That would be really nice. But remember, the prompt has only 1024 tokens. So that's not simply enough for the agent to learn anything. They use the word attend over. I couldn't quite figure out what that precisely means. It probably means it doesn't like have it in short-term attention or something like that. English is not my first language. I was a bit confused here in that the context, obviously you prefer to have as long context as possible, but the execution time, I've read somewhere and I couldn't quite find it, that the execution time grows quadratic in the context length. So you get much worse, and that's why they need to shorten it, and they can't just put it inside the prompt. Gato has to run within a 20 millisecond cycle due to constraints from the robotics. So that means that the running time must be really constrained, so the context has to be really small, so they have to work around this. However, it should be noted if you that the way it's actually described is in the robot that they are constrained on memory rather than on execution time. So it looks like both of these are actually hard constraints. So having to run it on a robot is a substantial problem. So the obvious thing you can do if you can't just edit in the prompt and hope for good meta learning is to fine tune on some demonstration, and that's obviously what they're doing. I think that's a very reasonable thing to do, and I think for all things that we care about, fine tuning is almost by definition going to be good enough. But I still think figuring out what it can do in meta learning is important. Like DeepMind probably thinks fine tuning is just fine, but I care a lot about how it, what kind of things it's capable of doing out of distribution, because those could potentially be unsafe. There was a comment on Twitter by someone called Jennifer saying that if Gato had achieved robust transfer learning, that's a technical success and not a safety failure, because the failure at transfer learning was not a safety plan because there is no safety plan. So that's a very negative view on DeepMind's work, and I think I probably endorse that. Let's have a look at these 4 tasks where generalization was attempted, where transfer learning was attempted. It was done at a smaller model, and the 4 called cardboard swing up, meter wall assembly, DM lab, water of apples forage, and Atari boxing. And again, you'll see on the y-axis we have performance, and the x-axis we have the number of fine-tuning episodes. They do this with 4 different runs. They have an expert run that is done by a reinforcement learning algorithm, which is like a line with something that is like they're trying to imitate this agent, distill this agent in some way, and so obviously we can't expect in general to have better results than the expert. And then they have an untrained model called Scratch, a model that is trained with like language understanding and images, but not with control data. And we remember that control data was like 85% of the training. And then they have some that has only been trained by the control, but not with language and images. And finally, one that's been trained with everything. And if we look at cardboard swing up first, as you probably would expect, using just a standard language model only starts to really make sense when you have like 1,000 fine-tuning episodes, and even then it could be kind of like an artifact. Teaching someone about language and images doesn't really help them to do cardboard swing up. You would want to do other control tasks. That does indeed seem to help, and in particular, if you have both of them, then, well, eyeballing this, it looks like it has better performance earlier to have both modalities of training, to have all modalities of training. So this is kind of the expected view. And there's another here where we can again see that the model trained from scratch takes a long while, but eventually actually ramps up. But the one that is trained by language, it can't do this assembly, this control task. And there seems to be like negative transfer in this case. It doesn't help, but again, having both kind of maybe, like, I feel perhaps I'm overinterpreting here, but it looks kind of like the yellow line is above the green. So having more data seems to help. There's another one here. Order of apples forage. In this case, it looks much more like this. Obviously, if you have control data, then you can easily get 19 of the apples. But even here, just having the language seems to somewhat help. It seems kind of clear that just that this helps compared to just having the scratch algorithm. And finally, for Atari, we see mixed results. I'd say, right? It's you could definitely argue that the red one, just from scratch, is just better. In that Atari is just so different from the others that fine-tuning on Atari helps, and doing pre-training on language and on control kind of doesn't really matter, as far as I can tell. Like, these lines are changing positions. It's not obvious what you can infer from this. So these are 4 very different cases, and I'm a bit sad that we don't have more than 4. Like, we can't really make any strong conclusions from this. Like, if I have to put on my conspiracy hat, I would say that they wanted to test it on 600 different tasks, and they had a set of tasks that was 604, and that meant they could only leave out 4. So I definitely think this work would have been much better if they had held out more than 4 tasks. So if we had seen 20 of these tasks, then it would have been interesting if they were all like Atari boxing or all like cardboard swing up. A criticism of this work was made on Less Wrong, not on Less Wrong, an interview with Blake Richards, a assistant professor at the University of Montreal, I think, claiming in this case that they're getting better transfer effects if you train in domain than if you train across all possible tasks. And like, this can be interpreted in 2 ways. They can be interpreted like, it's better to train in domain than in other tasks. That's the obvious thing, right? If you want to be good at control tasks, then training on other control tasks is better than training on language tasks. I mean, in that sense, that's probably really obvious. The other argument, however, is that you get better transfer effects if you only train on control and not train on language. So that would be the argument about what is, in general, from this, the relative position of the yellow line and the green line. And I would disagree with Blake Richards here in that, like, I really don't have a, like, it's hard to look at these images and say that the green line is above the yellow. That does not seem to be the case. It seems like there is some kind of transfer learning happening. Plausibly not in this Atari boxing, but again, remember with Atari, if you go back something like 3-4 years, there was the ALE, which was very, very famous for not having negative transfer. Back then, we always had negative transfer, and now we are seeing something that does not look like negative transfer, and that is indeed very surprising. Well, it's very surprising. Like, if you went back 4 or 5 years, that would be very surprising. We've seen this kind of thing many times recently, and it's no longer surprising. But we are certainly seeing some kind of generalization transfer learning happening. I think that is reasonably clear. Okay, so let's have another look at a real life skill. That's something that, of course, that's one of the key things that this paper is about, having also the robots actually do things in the real world and see how that works. In this case, they have a robot that picks up some cubes and stacks them, and have been trained on stacking the red cubes on top of the blue cubes. And that's the training task. And then the generalization task is then, can the robot figure out to put the blue cubes on top of the green cubes? Like, can they generalize from being really good at stacking red on blue to stacking blue on green? And they, of course, they can't do this in prompts, so they have to fine tune on that. And so they try that in simulation. And here the colors are different. There's a behavioral cloning algorithm and an expert reinforcement learning algorithm, and 3 models. You can see the blue one, the smallest model, picks it up relatively slowly, and the green one much faster, and the red one, the biggest model at 1.2 billion parameters, is much faster and even starts out better than the behavioral cloning algorithm. They do describe that there was one problem, one episode where overfitting was a problem, and that's the kind of thing that I always want from these papers, to actually dig into just one one interesting example. It would have been really interesting to see like what is actually going on in this particular episode that is problematic. But unfortunately, like papers don't like to give very, very concrete examples. And so they also, this was a simulation, and then they want to, like, how does this work in reality? And in this case, when they transfer this to reality, then Gato obtains a 60% success rate. 60% is this line, so that is to be expected. It seems like what Gato is doing transfers directly to reality. Then they try the behavioral cloning algorithm, and that totally fails to correspond to reality. It's this sim to real problem that a lot of algorithms have a surprising amount of difficulty going from simulations to reality. And in this case, it looks really markedly like 0.5% success is very, very bad. But they note qualitatively when the robot needs to stack up with the behavioral cloning, it seems like it's almost always doing the right thing, but then in the end, it's almost there, but then the tower collapses. Like this result here, like 60% compared to 0.5%, looks really, really wonderful, but this qualitatively, you can't really say that much because the bad algorithm gets it almost right every time. Okay, so now we look at how good can the robot actually get at stacking these boxes. And in this case, the thing we were trying before, it just joins into the training set and compares different algorithms, and they people who write these kind of papers always like to go into a huge amount of details about how they beat the state of the art. And you can look at it here, and they say this is even an earlier version of Gato that didn't use some fine tuning. I think I would have liked to have some kind of idea about how difficult is this task actually. They say that it took 20 seconds for a human to stack these with a 3D mouse, and the failure rate for humans is also like unknown. This is the kind of thing I would like to know. Like, are we talking about something that is above the human level or below the human level? I would like to know. The authors of Gato do more. They try to train some specialist single domain multitask agents. So within this control domain, they try to train it on all these things and nothing else, and see if they can like distill this into a general controller that is capable of doing all these tasks. And in MetaWorld, they're using one with 79 million parameters. And they managed to train on all these and distill into a single agent that has a success rate of 96.6, which is state of the art. At first, when I saw this, I was kind of surprised. Like 79 million parameters is not a lot these days. Like if you go back 3 years, sure it was a lot, but no longer, right? This is a really small thing, and I think it's surprising that it can learn that much with such a small model. I think I would almost argue that the transfer learning results we have seen have been really meager. Like the difference between the blue line and the green line we saw before were not very convincing to me. But this seems like some really neat distillation, and I think that's kind of surprising. But I also noticed that I am in fact a bit confused, because it states here that it beats the state of the art with taking a small model and just fine-tuning it in the most naive way, and then you get something that is wonderfully good and beats the state of the art. And I'm wondering, like, what was the state of the art before, right? Why it's not clear what they're doing that is so smart that they can take a small model and just distill it in the most obvious way and beat state of the art. Normally you need to do something smart, really smart, to beat state of the art, right? Then they also have the Atari problems, where they use the full model, and they social demonstrations had some kind of problem. It was not entirely clear to me what it was, but in the rest of them, the 44 out of 51, they had gain to perform above the human level, and even without any kind of fine-tuning. 23 of the 51 Atari games had superhuman performance, and they expected just scaling would improve this. Um, the problems with training can be summarized as the specialist Atari agent achieved better than human performance for all games where data contains superhuman episodes. Again, because they're not directly doing reinforcement learning, they are distilling other reinforcement learning algorithms. Then there's a section called related work. I won't call it related work because what they're actually doing is trying to make some kind of argument about why this will scale. And so I just as an illustration of scaling, I took this classic graph from Jared Kaplan's scaling law. So why do we expect this will scale? Well, obviously we have substantial experience with the models that are larger than 1.2 billion. Like we have GPT-3 most obviously, but also many others, and like more models are arriving or every week, I would almost say. So that's a good argument for why this will scale. And we've also seen like good results in general with these kind of ultra aggressive models. We are seeing this perform very well in many other circumstances, and that's also an argument why we should expect this to transfer. And this is the first single generalist trained on hundreds of vision, language, and control tasks using modern transformer networks at scale. I'm somewhat confused that yeah, I mean, sure, it's the first one that has done this, but it seems like I should be careful about calling it naive and obvious and all these kind of things because I can't do it myself, right? They have some more arguments, a bit more fluffy, like the brain seems to have like a uniform structure, and that's kind of an argument why you don't need different things for like motor control and processing visual, because if you break some of the motor control, then the motor control can just move into the visual area. That's great. And we're also seeing this with neural network, that everything can be processed everywhere, and that's like an argument for some kind of transfer learning. Finally, they talk a bit about why this Atari might be more difficult than many other tasks. And I mean, conceptually, a lot of control tasks and a lot of robots are working in reality, whatever that may mean. And so reality, like having a robot that is big or small or doing different kind of things, they have like the physical underlying structure, and Atari games doesn't share any kind of underlying structure in the same way as reality does. Finally, they talk about the implications for AI safety. And so I tried to look up DeepMind and safety, and I got this wonderful result from Google with DeepMind's Twitter and then missing safety, and Google suggested I could repeat my query with the word safety, because the word safety is not one that DeepMind is using at all. And they say that, yeah, this is safety seems to be an important thing, and someone ought to look into this. And I think I've read enough papers to realize that this kind of call for action is just, empty words. They're saying that, yeah, it would be nice if someone did this. We will take no action towards doing anything further. And as problematic is the fact that when they talk about safety, the examples that they give about safety are things that are not actually related to safety as we conceptualize it, but lack of capabilities, in the obvious sense that an agent can be unsafe because it is trying to do the right thing, it's just not capable of doing the right thing, compared to an agent trying to competently optimize for something we don't want. It's not completely fair. They do, in fact, mention Stuart Russell a little. So it's not 100% that they only look at capability, but it's a weak chapter, this. And they also have seem convinced that this safety isn't actually any kind of meaningful problem. They are very optimistic about solving that, and I think in my estimate, this if you conceptualize safety as a race between capability and safety alignment work, then this work seems clearly to be advancing the state of AGI and building height towards AGI. It seems obviously on net as a strong negative. zooming out a bit, is DeepMind in fact on track to destroy the world? I think definitely this paper seems like it is not trying very hard to engage with this or trying to in any way look into this, whether we humans end up with a better strategic situation or a worse strategic situation. And in my analysis, it kind of depends. It's not obvious to me that this is a big step towards AGI. Like multimodal transformers, how important are they actually going to be? That's an interesting question, and it's not obvious to me at all that they will turn out to be very interesting. That it's possible that just plain learning on text is sufficient, and images, and soon we'll probably have video. Maybe that might not matter very much. How about transformer agents? How important are they going to be compared to just decoder only transformers? Again, it's an open question. I don't know. It's not obvious to me that transformer agents is going to have a much larger impact than just GPT-3 or something like that. But it's not. It's also not obvious that it won't have. So this is the kind of thing that I would focus on trying to determine whether this work is in fact having a substantial positive or negative, or well, whether it has a small impact or a substantial negative impact. Another thing that would have been nice and would have been possible to do with this work would be interpretability work. Like in particular, some of the models are really small, 39 million neurons. Seem like it would be easier to do interpretability work, but apparently, as far as I could tell from this, no such work was done at all. And finally, there is a quick reference to the book Superintelligence, saying that many embodiments make technical AGI safety more difficult. And that's cited as Nick Bostrom's Superintelligence, Donut 2017. And I have the book and I've read it several times, and it does in fact not say this. And also, like, the Donut is the French book distributor, I think, which I don't think that's a correct citation. But that is like the smallest nit to pick. That is all for today. Thank you and see you next week.